somewhere beneath the ice sheets of Antarctica, buried under layers of frozen snow that took hundreds of thousands of years to pile up, there is a clock. Not a clock with hands or a digital display, but a clock written in bubbles of ancient air, in microscopic crystals, in the chemical signatures of temperatures that existed before our species took its first breath. And what that clock tells us is one of the strangest, most humbling things science has ever discovered. Earth has been falling into deep freezes over and over on something close to a regular beat. Not randomly, not chaotically, but rhythmically, almost like a pulse. Ice. Then warmth, then ice again, and again, and again, for millions of years. Now, here's the question that has quietly obsessed geologists, astronomers, climatologists, and evolutionary biologists for well over a century. Why roughly every 100,000 years? What is setting that timer? What is the mechanism behind a planet-wide freeze that comes and goes with something approaching clockwork precision? And maybe most importantly for us, what did that rhythm do to the small, vulnerable, extraordinarily stubborn species that was trying to survive inside it? That last question is the one that keeps pulling you deeper into this story. Because it turns out the ice ages weren't just a backdrop to human history. They weren't just bad weather on a geological scale. They shaped us. They pushed our ancestors into corners, forced them into innovation, carved the geography of the world we inherited, and may have had more to do with who we became than almost anything else you can name. Before we get there, if you're already feeling that pull towards sleep, that's exactly the point. These episodes are designed to take you somewhere fascinating and let your mind drift off inside a story worth dreaming about. So if you're new here, consider subscribing. And if you want these with no ads and no music, completely clean audio, you can follow the channel on Spotify. The link is in the description. It's free, it's easy, and it helps keep this going. Now, where are you right now, and what time is it? Drop it in the comments. I genuinely read them. There's something surreal about knowing someone in Edinburgh is drifting off at 2 a.m, while someone in Melbourne is folding laundry at 7 p.m, both thinking about ice ages. The geography of this audience is its own kind of fascinating map. So back to the ice. Here's the thing that makes this mystery so strange from the very beginning. The timing isn't perfect. It's not like a metronome ticking out exactly 100,000 years between each glaciation. It's more like a heartbeat in a sleeping person, close, recognizable, but with variation. Some cycles ran a little longer, some a little shorter. And before about 900,000 years ago, the rhythm was completely different. The world was freezing and thawing on a 41,000-year cycle instead, which is itself a strange and specific number that will make a lot more sense once we dig into the astronomy. That shift from 41,000 years to 100,000 years, right around 900,000 years ago, is called the mid-pleistocene transition. And it is one of the most puzzling and consequential climate events in Earth's recent history. Because scientists still don't have a complete, universally agreed upon explanation for why it happened. The leading theories are fascinating, and we'll go through them carefully. But the honest answer is that this is a mystery science has made enormous progress on without fully closing. What we do know is that the shift to longer, deeper ice ages happening right around that 900,000-year mark lines up almost exactly with a period you might already know something about, depending on whether you've been with this channel for a while. That's the same general window when early human populations appear to have gone through a catastrophic population crash, a bottleneck so severe that our ancestors were reduced to numbers too small to seem survivable. The climate didn't just get harder around 900,000 years ago. It reorganized itself into something far more brutal. Throughout this journey, we're going to follow the evidence the way scientists actually found it, which means working backward from what we can measure today. We'll look at the ice cores pulled from Antarctica and Greenland, cylinders of frozen time that trap actual air from ancient atmospheres. We'll look at the ocean floor sediments that record sea temperatures going back millions of years. We'll trace the astronomical theories, the orbital mechanics of Earth's path around the Sun, that a Serbian mathematician spent decades working out in the early 20th century. And we'll look at the feedback loops, the ways that ice creates more ice, the way carbon dioxide acts as a slow amplifier, the way oceans store and release heat on timescales that make human civilization look like a blink. And woven through all of that, we'll keep coming back to the human thread. Because the ice ages didn't just happen to rocks and ocean currents. They happened to people. They determined which land bridges existed and which didn't, which coastlines were accessible and which were buried under glaciers, which ecosystems thrived and which collapsed. They may have driven some of the most critical leaps in human cognition and technology, not by making life easier, but by making it brutally, relentlessly hard. There's something quietly extraordinary about the fact that you can trace a line from the eccentricity of Earth's orbit around the Sun, a slow wobble in the shape of our path through space, all the way down to decisions made by a small group of early humans huddled around a fire somewhere in Africa, trying to survive another generation. That line exists, the evidence for it is real, and following it is one of the more remarkable intellectual journeys available to anyone willing to pay attention. So get comfortable. Let the weight of the day ease off. We're going back a very long way, and the story is worth every step. The first person to seriously suspect that ice had once covered most of Europe didn't arrive at that idea by looking at glaciers. He arrived at it by looking at rocks, specifically at rocks that had no business being where they were. These are called erratics, boulders, sometimes enormous ones, sitting in the middle of flat plains or perched on hillsides, completely unlike anything in the local geology. A chunk of granite sitting in a valley of limestone. A massive stone the size of a house resting on open farmland in northern Germany, composed of rock that only occurs hundreds of miles away in Scandinavia. For centuries, farmers and travellers noticed these things and moved on. The educated explanation, if anyone bothered to give one, was Noah's flood. A great deluge had swept the boulders into position and deposited them there when the waters receded. It was tidy, it fit existing frameworks, and it was almost certainly wrong. The person who began unravelling the flood explanation was a Swiss naturalist named Louis Agassiz, though the idea had been gestured at by others before him. In the 1830s, Agassiz spent time in the Alps studying living glaciers, watching how they moved, watching the marks they left behind. And he noticed something that would turn out to be enormously important. Glaciers are not passive things. They carry. They grind. They gouge long parallel scratches into bedrock that you can still see clearly after the ice is long gone. They push sediment into ridges at their edges, ridges called moraines which persist in the landscape for thousands of years after the ice retreats. And they transport boulders, sometimes carrying them dozens or hundreds of miles before depositing them in places where nothing else could explain their presence. When Agassiz looked at the landscapes of northern Europe and Scandinavia, and later North America, he didn't just see isolated erratics. He saw the full signature. The scratched bedrock, the ancient moraines running across the land like the frozen wave crests of some impossibly slow tide. The systematic pattern of sediment distribution that only made sense if enormous rivers of ice had once flowed across these regions and then melted away. In 1837 he proposed something that struck most of his contemporaries as almost insane. There had been an ice age, not just in the high Alps, but across vast regions of the northern hemisphere. Ice sheets comparable to the one currently sitting on Greenland had once smothered Britain, northern Germany, Scandinavia, and much of North America. The backlash was fierce. Respected geologists argued against it for years. The flood hypothesis had deep roots, partly scientific and partly cultural, and it didn't yield easily. but the physical evidence was simply too coherent to dismiss forever. By the 1860s, the idea of past glaciation had become widely accepted in principle. What took much longer was the question of whether it had happened once or many times. This is where things get genuinely complicated and where the first real suspicion of a repeating pattern began to form. Because as geologists examined glacial deposits more carefully across Europe and North America, they started noticing something strange. The sediment layers didn't tell a simple story of ice advancing and then retreating. They told a layered story. You would find a layer of glacial till the unsorted mixture of clay, sand and boulders that glaciers leave behind, and then beneath it, or interspersed within it, you would find something else entirely. Soil layers, peat deposits, the fossilized remains of plants and beetles and pollen from species that only live in warm climates. And then more glacial till below that. This stratigraphy, the sequence of layers reading backward through time, suggested something remarkable. The ice had come more than once. There had been warm intervals between glaciations, periods warm enough to grow trees and support temperate ecosystems in regions that were later buried under ice again. The ice ages were not a single ancient freeze followed by a gradual thaw. They were episodes in a recurring cycle. By the late 19th century, European geologists had begun naming distinct glacial stages. Working primarily through the Alps, a framework emerged identifying what appeared to be 4 major glaciations, which were given names that sound almost poetic now. The Gunz, the Mindel, the Riss, and the Würm. North American geologists developed their own parallel sequence with different names. The Nebraska, the Kansan, the Illinoisan, the Wisconsinan. These were not perfect equivalents across continents, and the correlation between them required decades of argument and revision. But the basic framework was the same on both sides of the Atlantic. Multiple glaciations had happened. There was a rhythm to it, even if nobody yet knew the precise timing or the mechanism behind it. The challenge that haunted all of this early work was the problem of deep time. How do you know when something happened if you have no reliable clock? The glacial deposits themselves could tell you relative order, which layer came before which moraine was older than which other moraine. But turning relative sequence into actual dates, actual years, was enormously difficult before radiometric dating methods were developed in the 20th century. Early estimates of glacial timing were based on things like rates of river erosion and the thickness of sediment deposits, methods that gave rough guesses rather than reliable dates. Some researchers in the early 20th century estimated the last glaciation had ended perhaps 10 or 15,000 years ago, which turned out to be roughly correct. But estimates for older glaciations varied enormously, sometimes by hundreds of thousands of years. Despite this, the suspicion that a repeating rhythm was driving these cycles took root long before anyone had the tools to measure it precisely. The very regularity of the pattern, 4 major glaciations in Europe, 4 major glaciations in North America, separated by warmer interglacials, implied something systematic was going on, something cyclic, something perhaps driven by forces that operated on a planetary or even astronomical scale, rather than just local geology or ocean currents. The person who pushed hardest toward an astronomical explanation was a Scottish journalist and self-taught scientist named James Croll, working in the 1860s and 1870s. Croll had noticed that Earth's orbit around the Sun is not a perfect circle. It's an ellipse, and the shape of that ellipse changes slowly over time in predictable ways. He calculated that these orbital variations would alter how much sunlight the northern and southern hemispheres received at different times of year, and he proposed that ice ages were triggered during periods when the northern hemisphere received less solar energy during summer. Less summer warmth meant last winter's snow didn't fully melt, which meant it accumulated year after year, which eventually meant glaciers. The idea was compelling, though Kroll's specific timing predictions turned out to be off. and the scientific community was skeptical. But the seed was planted, the notion that something external to Earth itself, something in the geometry of its orbit around the Sun, could be setting a tempo for climate cycles, was now in circulation. It would take another 50 years and a Serbian mathematician named Milankovitch to develop the calculations into something rigorous enough to take seriously, and even longer before anyone had the data to test those calculations properly. That's a story for later in this journey. What matters right now is that by the early decades of the 20th century, a picture had assembled itself through patient observation, argument, and geological detective work. Earth had experienced multiple ice ages. They had come and gone in something that looked like a pattern. The pattern was almost certainly driven by something cyclic and possibly astronomical, and the pattern had profoundly reorganized the surface of the planet each time it played out. But the evidence assembled so far was fragmentary. It was built from surface observations from moraines and erratics and pollen layers, from sequences of sediment read out of riverbanks and quarry walls. The glaciers covered and then erased their own earlier evidence with each new advance, making older glaciations progressively harder to read. You could trace the most recent glaciation in reasonable detail. The earlier ones were blurrier. The ones before that were blurrier still, their evidence largely overwritten by everything that came after. To truly read the full rhythm, to see not just 4 rough stages, but the actual pulse of dozens of cycles playing out over millions of years, scientists were going to need a different kind of archive, one that hadn't been scraped clean and rearranged by the glaciers themselves. One that had simply accumulated layer by layer undisturbed, preserving the record of every warm period and every cold one in a continuous sequence stretching back millions of years. That archive existed. It was sitting at the bottom of the ocean, and it was going to change everything. Before we go down to the sea floor to read that archive, we need to clear up a quiet confusion that sits behind almost every discussion of climate history. When people say the Ice Age, they usually mean one thing. Scientists usually mean something else. In everyday language, the Ice Age is that time, sometime in the distant past, when mammoths wandered across frozen Europe and humans in fur clothing huddled in caves while walls of ice loomed just over the horizon. It sounds like a single era, one long winter that eventually ended and gave us the mild, green world we live in now. But in climate science, that's not what an ice age is. In that technical sense, an ice age is any long interval of Earth history, when permanent ice exists at the poles or on large continents. It isn't a brief cold spell. It isn't a century of bad winters. It's a background state of the planet, a mode it can occupy for millions of years at a time. By that definition, we are still in an ice age right now. You can walk outside on a summer afternoon, feel the heat on your skin, and you are still living in an ice age, because there are great ice sheets locked over Greenland and Antarctica. They are smaller than they have been at many times in the past few million years, but they exist. They are permanent on human timescales. That's the only requirement. Inside that broad ice age state, climate slides back and forth between 2 distinct configurations. One is what you're living in, a relatively warm interval known as an interglacial. The other is what most people picture when they imagine the Ice Age, a glacial period. This is where the terminology gets slippery. Ice Age in popular speech usually means glacial period in scientific speech. But the glacial periods are really just the cold beats in a longer icy rhythm. They are episodes within an ongoing ice age, not the entire composition. For the last 2.6 million years or so, since the beginning of what geologists call the Quaternary period, Earth has been locked in one of these icehouse states. Before that, through most of the age of dinosaurs and much of the age of early mammals, it was the opposite. A greenhouse world with no permanent ice caps, high sea levels and warm forests or scrublands stretching almost to the poles. The transition into the Quaternary icehouse isn't fully understood, but by 2.6 million years ago the pattern is clear. Ice had settled onto Greenland and Antarctica for the long haul. From that point to the present, the overall background is cold compared to most of the last 500 million years. Yet within that cold background the climate swings. Think of it like a person breathing. The icehouse condition is the person itself, alive and present for millions of years. Glacial periods and interglacials are the slow inhales and exhales. The lungs expand, the lungs contract. Ice sheets grow, ice sheets shrink. But as long as polar ice never fully disappears, the underlying state is the same, an ice age. During a glacial period, the kind that left erratics scattered across the fields of Germany and the plains of North America, the differences from today were gigantic. Global average temperatures were perhaps 4 to 6 degrees Celsius lower than modern values. That doesn't sound like much when you're used to day-to-day swings of 10 degrees, but averaged across the whole planet, it's transformative. At the height of the last glacial period around 20,000 years ago, so much water was locked up in continent-spanning ice sheets that global sea level dropped by roughly 120 meters, about 400 feet. Coastlines marched outward. The North Sea was dry land. The English Channel was a river valley. What is now Indonesia and the shallow seas around it fused into a single vast landmass stretching from mainland Asia down toward Australia. The Bering Strait between Siberia and Alaska was a broad, cold steppe you could walk across. Forests and deserts moved as if they were alive. In many temperate regions that are now covered in broadleaf woods or farmland, cold-adapted grasslands and sparse tundra vegetation took over. The Amazon rainforest shrank and fragmented. Tropical belts narrowed. Great belts of desert expanded in some latitudes and retreated in others, responding to shifts in rainfall as the atmospheric circulation reorganized itself around the new temperature gradients. Then, in an interglacial like the present, much of that reverses. Ice sheets retreat into their cores. Sea level rises, often by more than 100 meters. Drowned river valleys become estuaries and bays. Those temporary land bridges vanish under shallow seas. Forests advance poleward. Tropical rain belts widen and thicken. Coasts erode and redraw themselves, carving new islands and peninsulas out of what, only a geological moment before, had been high ground. The world does not simply get warmer or colder in place. The entire map breathes. Shorelines, deserts, forests, grasslands, all slide back and forth between two differently arranged versions of the same planet. To people living through these changes, though, it would not have felt like a single global switch being flipped. It would have felt stubbornly local. If you were a hunter in what is now southern France, watching winters lengthen and summers cool, your reference frame is the forest on the hill behind your camp, the river in the valley, the migration paths of the herds you follow. You notice that the tree line is creeping downslope, that snow lingers a little longer each spring, that certain plants no longer grow in places they once did. You do not see the coasts of Southeast Asia marching 100 kilometers outward. You do not see the Sahara breathing in and out. You see your valley. This is one reason our written myths remember floods and droughts and regional famines much more vividly than they remember the slow glacial dance. Human societies experience climate through local weather, local crops, local water. The driver may be global, but its imprint is etched into 1 million distinct landscapes, each responding according to its own geography. And yet, when we step back and assemble all those local reactions into a single story, a more unified pattern emerges. One of the most striking features of that pattern is asymmetry in time. Across many different climate records, from ocean sediments to ice cores to cave stalagmites, the glacial cycles show a consistent shape. The descent into a full glacial is long and gradual. Temperatures drift downward step by step. Ice sheets grow, withdraw a little, then grow further. Sea level ratchets down in a series of small drops. It can take tens of thousands of years for a glacial period to fully build. The exit is different. The warming at the end of a glacial is often abrupt, geologically speaking. In a few thousand years, sometimes less, temperatures leap upward, ice sheets collapse, and sea level surges. Climate scientists sometimes talk about this as slow build, fast collapse, a staircase down into the cold, an elevator ride back up toward warmth. Why does it work that way? What sets the basic timing of these breaths of ice? Why are we living in a relatively brief warm interglacial, rather than in the long grinding descent or the icy bottom? Those questions lead directly to the astronomical idea that James Kroll had begun to sketch in the 19th century, to the notion that Earth's orbit itself might be the metronome behind these slow, dramatic swings. To see whether that could possibly be true, scientists had to find a climate record long enough and precise enough to capture not just 4 big glaciations, but dozens of cycles. They had to find a clock buried not in scattered boulders on the continents, but in something that had quietly, patiently recorded every pulse of the quaternary icehouse world. For that, they turned to the ocean floor. The notion that the orbit might be the clock was older than the data that could test it. In the late 19th and early 20th centuries, before anyone had drilled an ice core or mapped the sea floor, a few mathematically inclined minds were already staring up at the sky and then back down at the glacial debris on Earth, wondering if the two could possibly be linked. One of those people was a Serbian engineer working in relative obscurity, calculating the changing geometry of Earth's path around the Sun with a patience that bordered on obsession. His name was Milankovitch. Milankovitch did not think the Sun itself was changing much over these timescales. There was no mysterious dimming and brightening of the star. Instead, he proposed something subtler. The way Earth orbits the Sun and the way it spins are not fixed. They wobble, they stretch, they tilt. Over tens and hundreds of thousands of years, those slow mechanical motions change the pattern of sunlight falling across the planet. Not the total energy over a whole year, averaged across every latitude. That barely changes. What changes is where and when the sunlight arrives. How intense summer is at 50 or 60 degrees north. How long winters last at the edge of an ice sheet. Whether snow that falls in one year has any realistic chance of surviving into the next. To Milankovitch, this was the key. Ice sheets do not care about global annual averages. They care about summers in the places where they live. You can think of his theory as a kind of celestial irrigation schedule. The orbit does not turn the sun up or down. It turns the spray of sunlight back and forth across the surface, sometimes pouring more into northern summers, sometimes taking it away, and in doing so it controls whether high-latitude snow and ice melt away or quietly accumulate. He formalized this idea in terms of 3 distinct rhythms. The first is eccentricity, the shape of Earth's orbit. Right now, the orbit is almost a circle, but not quite. Over cycles of roughly 100,000 and 400,000 years, gravitational tugs from Jupiter and Saturn slowly stretch and relax that shape, making it slightly more or less elliptical. When the orbit is more eccentric, Earth spends part of its year noticeably closer to the Sun and part noticeably farther away. When it is more circular, that difference shrinks. The second is obliquity, the tilt of Earth's axis. Imagine a spinning top, not standing upright but leaning. Earth leans about 23.5 degrees relative to the plane of its orbit. That lean is what gives us seasons. Over about 41,000 years, the tilt rocks back and forth between roughly 22 and 24.5 degrees. A greater tilt means stronger seasons, hotter summers and colder winters, especially toward the poles. A smaller tilt softens the seasons, making summers less scorching, winters less brutal. The third is precession, the slow wobble of the spinning axis itself. If you've ever watched a top starting to lose speed, you've seen precession. Earth's axis traces out a circle in the sky over about 23,000 years. Combined with eccentricity, this wobble changes the timing of the seasons relative to where Earth is on its slightly elliptical orbit. Over these cycles, a given hemisphere's summer can occur near the closest point to the Sun, making it intense, or near the farthest point, making it mild. Eccentricity sets how different those distances can be. Obliquity sets how strongly tilted the poles are into or out of the sunlight. Precession slides the seasons around on that orbital track. Milankovitch did something remarkable for his time. Using hand calculations and the best orbital mechanics available, he worked out how each of these cycles would change the amount of solar energy falling on different latitudes at different times of year over hundreds of thousands of years. Then he focused on one measure: summer insolation at high northern latitudes. Why there? Because that is where the big ice sheets of the last few million years had lived. Not over Antarctica, sitting on a continent surrounded by ocean, but over North America and Eurasia, where land masses reach deep into the high latitudes of the northern hemisphere. He reasoned that what matters for ice is not how cold the coldest month gets, but how warm the warmest months become. Snow can pile up every winter, but if summer sunshine is strong enough, it will melt back down. For an ice sheet to grow, some part of that winter snow has to survive the summer and turn into firn, then glacial ice, year after year. To shrink an ice sheet, you don't have to make winters warmer. You just have to make summers bright and long enough that the ice melts faster than it is replenished. So he calculated the history of summer sunlight at, say, 65 degrees north, over the last several 100,000 years. The result was not random. It oscillated in clear, regular cycles, a combination of those orbital rhythms beating together. Sometimes high-latitude summers were weak, with relatively little sunlight. Sometimes they were strong. If those weak summer intervals tended to line up with glacial advances, and strong summer intervals with retreats, then the orbit could indeed be the metronome. On paper, it was an elegant, almost hypnotically satisfying idea. Cold summers in the north let snow survive year to year. Ice thickens, brightens the planet, cools it further. Warm summers carve back the ice. The celestial gears above set the pace. The ice sheets respond below. But there was a problem. Milankovitch was building his clock before anyone had a clear, continuous record of the ticks. The data available to him were crude, a handful of glacial deposits dated with large uncertainties, some scattered estimates of past temperatures, a rough sense that there had been 4 great glaciations in Europe, trying to match that patchy, local and often misstated evidence to the smooth orbital curves was like trying to synchronize a symphony using a few smudged notes on a napkin. Many geologists and climatologists admired the mathematics and ignored the conclusions. The physics seemed reasonable, the numbers looked neat, but the Earth record, as then understood, did not obviously sing the same tune. Some glaciations seemed out of phase with his predicted low summer insolation intervals. Others were missing entirely. If this really was the master climate clock, why did the hands on the geological dial look so messy? There was another source of unease. The cycles of tilt and wobble and orbit change the distribution of sunlight, but the raw energy difference they create is relatively small. A few percent more or less summer insolation at a given latitude does not sound like enough to drag the planet from lush interglacial into kilometre-thick ice and back again. In other words, even if the timing worked out, the mechanism looked weak. An astronomer's nudge, not a geologist's hammer. Milankovitch himself understood this. He never claimed orbital forcing acted in isolation. He imagined the ice sheets, the oceans, the atmosphere, and even carbon dioxide in the air responding to that gentle celestial push, amplifying it through feedbacks. White ice reflecting more sunlight, cold oceans taking up more CO2, changing circulation patterns that shifted rainfall and storm tracks. The orbit would be the rhythm section, but the climate system would be the orchestra. Still, without a long, precise climate record to compare against, the theory stayed in a kind of limbo. Beautiful, plausible and unproven. Too tidy for some geologists, too geologic for some astronomers, it hovered at the edge of mainstream acceptance. What it needed was an independent, high-resolution archive of past climate, stretching back more than 1 million years, with dates accurate enough to catch those subtle celestial beats. An archive that did not care about political borders or the luck of where glaciers had left their rubble. The answer to that need lay not in mountain valleys or scattered moraines, but in the slow rain of shells and dust sinking year after year to the bottom of the world's oceans. Far from the shifting shorelines and bulldozing ice, the deep ocean was keeping its own quiet minutes. Every time a tiny planktonic organism built a shell and died, that shell began a slow fall. Down through dim blue water past drifting snowflakes of organic debris, into the darkness where no storm could reach. It settled onto a seabed that barely noticed human timescales. Millimetre by millimetre, those shells made a layered archive older than any human lineage. By the mid-20th century, oceanographers had started to realize that this mud might be the climate record Milankovitch needed but never saw. If you drag a coring tube into the deep sea and punch it into the sediment, what you recover is a cylinder of time. The topmost layer is recent, a few decades or centuries old. Deeper down, you move back through tens of thousands, then hundreds of thousands of years, each centimetre representing a slice of history. The details depend on how fast sediment accumulates, but the basic idea is simple. Continuous deposition, far from the erosive chaos of land. At first, researchers looked at these cores the way geologists had looked at rocks for generations. They counted and identified the fossils of microscopic plankton, tracked which species appeared and disappeared, and tried to infer broad climatic changes, warm versus cold, nutrient-rich versus nutrient-poor. But there was a more direct signal hidden in those shells. Not just which organisms lived, but what kind of water they had grown in. The key lay in oxygen itself. Oxygen comes in different isotopic flavours. The most common is oxygen-16, with 8 protons and 8 neutrons. Rarer is oxygen-18 with 2 extra neutrons. Chemically they behave almost identically, but physically, the lighter form is just a bit easier to evaporate, to move around, to lift into clouds. When water evaporates from the ocean, the molecules containing oxygen, 16 escape, a little more readily into the atmosphere. When that moisture moves over land and falls as snow that later becomes ice, it locks up a disproportionate amount of oxygen, 16, on the continents. What does that do to the oceans left behind? It enriches them in oxygen-18. Now imagine huge ice sheets growing on land. They are, in effect, giant storage vaults for oxygen-16. The more ice you pile up, the more you strip the ocean of its light isotope, and the heavier its oxygen signature becomes. When global ice volume shrinks during a warm period, that stored oxygen-16 melts back into the sea, and the ocean's isotopic balance tips back toward lighter values. Plankton building calcium carbonate shells in that water faithfully record the ratio of oxygen-18 to oxygen-16 in the carbonate they precipitate. Decades later, scientists can measure that ratio with mass spectrometers to a precision Milankovitch could only have dreamed of. Those measurements became known as delta, or the 8O delta OTene, a tiny numerical shift that encodes a world of ice. Higher delta 30 U in foraminifera shells generally means more global ice volume and often cooler deep ocean temperatures. Lower delta 30 FERT means less ice, warmer conditions. There are complications. Temperature itself also affects fractionation, Regional salinity can matter, but as a first approximation, Delft-Thurth-Oat is a remarkably good dial for reading the waxing and waning of ice sheets over geological time. By the 1960s and 70s, researchers like Cesare Emiliani, Nicholas Shackleton and others began to assemble long Devo records from deep-sea cores around the world. They plotted these ratios down core against depth, then against age estimates based on sedimentation rates and the occasional volcanic ash layer, or magnetic reversal. What emerged was not a random scribble, but a sawtooth pattern repeating over and over. Gradual increases in delton of Herteth Earth as slow growth of global ice volume were followed by sharper drops, signalling relatively rapid meltbacks. Cold, icy episodes and warmer interludes alternated in a rhythm that stretched far beyond the 4 neat glaciations once imagined from European landforms. Paleoclimatologists started to divide this fluctuating record into numbered intervals, odd and even, called marine isotope stages, MIS for short. Odd numbers for warmer, low ice periods, even numbers for colder, high ice ones. MIS 1 is the present interglacial. MIS 2 is the last glacial maximum, around 20,000 years ago. Below that, the numbers count backward through time, each step representing a new chapter in Earth's changing climate. For the first time, there was a continuous global-scale picture of glacial cycles stretching back hundreds of thousands of years, and then beyond 1 million. The real power of this oceanic archive became clear when cores from distant parts of the world were compared. Sediment from the North Atlantic, the South Atlantic, the Indian Ocean, the Pacific, very different basins, different circulation patterns, different ecological histories, yet the broad up and down swings in Delton 30 NATO lined up. When one core showed a high Delton 30 peak indicating a major glacial, so did the others with only small time offsets. When one recorded a sharp transition to a warmer low ice state, echoes of that transition appeared across the global network of cores. The deep ocean, it turned out, is well mixed on timescales of 1,000 years or so. The water that bathes the sea floor in the Atlantic eventually circulates into the Indian and the Pacific. As it does, it carries with it a near global average of the planet's isotopic state. Local quirks exist, but the underlying signal is planetary. This interocean agreement did something important. It transformed the Delton 30O curve from a regional curiosity into a global climate index. If the same pattern appeared in multiple basins, using different cores extracted and measured by different labs, it was unlikely to be a fluke. And within that global curve, a pacing began to stand out. In the more recent part of the record, say the last 800,000 or 900,000 years, the big swings between full glacial and full interglacial seemed to fall roughly every 100,000 years or so. Not perfectly, not like clockwork, but often enough that the spacing could not be ignored. Earlier in the cores, farther down in time, the oscillations appeared more frequent and smaller, closer to a 40-odd thousand-year rhythm. Here, in the mud at the bottom of the sea, was a climate metronome. Its beat was not simple, but it was there, and it echoed the orbital periods Milankovitch had calculated. The 41,000-year tilt cycle, the 23,000-year precession, and something at or near 100,000 years that seemed to organize the largest glacial shifts. Yet, even as excitement grew, caution remained necessary. Dating deep-sea cores is not easy. Before more sophisticated methods emerged, age models often relied on assuming roughly constant sedimentation rates, then tweaking them to line up visible features with known events such as magnetic reversals or specific ash layers. That introduced uncertainties of many thousands of years, especially farther back in time. Interpreting Delton of O itself also sparked debate. How much of a given shift reflected ice volume, and how much reflected deep ocean temperature changes? Were all the marine isotope stages truly global, or could some be regional expressions of circulation changes? Different laboratories sometimes reported slightly different values from the same horizons, highlighting methodological sensitivities. The temporal resolution was another limitation. In many places, a centimetre of sediment might represent 1,000 years or more. Short, abrupt events could be smeared together, blended into a single data point. The cores were excellent at capturing long, slow swings, less so at resolving the finer details within them. Despite these caveats, the broad pattern was hard to dismiss. Here was a continuous climate record, spanning more than 10 times the length of human history, showing regular, quasi-periodic shifts that looked uncannily like an orbital fingerprint. The oceans, indifferent to human curiosity, had recorded every glacial breath and interglacial sigh. All that remained was to match those breaths to the subtle rhythm of the sky, and to ask why, at some point, the beat seemed to change. To answer that, scientists had to look for an archive that offered even sharper slices of time, one where individual centuries and even decades could be teased apart, and where the breathing of the climate could be measured not only in the weight of ocean water, but in the very composition of the air itself. On the great ice sheets of Antarctica and Greenland, snow falls like a whisper and never quite leaves. Each winter adds a thin new layer. Each summer, wind and weak sunlight reshape the surface. But in the coldest central regions, nothing melts enough to erase the past. Year after year, the snow stacks up. Under its own weight, it slowly compresses, squeezing the air out of the spaces between flakes, welding them into solid ice. But it doesn't lose all the air. Before those snowflakes fully fuse, the spaces between them trap tiny pockets of the atmosphere. Over decades, then centuries, those pockets are sealed off from the surface. They become bubbles of ancient air entombed at depth. If the deep-sea cores are cylinders of mud that remember the weight of ice on the oceans, these polar ice sheets are lungs. They have been quietly inhaling and exhaling the planet's atmosphere for hundreds of thousands of years and saving a sample from every breath. By the mid-20th century, a few glaciologists began to imagine what might happen if you drilled down through that frozen archive. The first attempts were crude, shallow holes a few tens of meters deep, capturing only the most recent centuries. But as drilling technology improved, so did ambition. Teams moved to the coldest, driest, most stable parts of Antarctica and central Greenland, places where snow had been falling more or less continuously for a very long time. The deeper they drilled, the further back in time they went. Unlike the ocean sediments, where each centimetre might blur a millennium together, some sections of ice preserve annual layers you can count. A slightly dusty band for a windy springtime storm. A cleaner, brighter band for a calm winter's snow. In Greenland especially, those seasonal rhythms can be read like the rings of a tree, year by year, storm by storm. Farther down, compression smears the individual years together, but the order remains intact. Millennial scale history, preserved with the regularity of a metronome. Within that layered ice, two kinds of information are especially important. The first is locked in the ice crystals themselves. The ratio of oxygen isotopes again, delton 30O, or of deuterium, a heavy form of hydrogen, shifts with temperature. Colder conditions tend to favour one isotopic mix, warmer conditions another. Measure those ratios up and down the core, and you sketch a temperature history for the region where the snow fell. The second is in those sealed bubbles, unlike the isotopes, which are proxies that must be interpreted. The gas in those bubbles is literally ancient air. It contains carbon dioxide, methane, nitrous oxide, argon, nitrogen, oxygen, a miniature atmosphere from the year that snow was laid down. Melt a bit of ice from 20,000 years ago in a vacuum chamber, crack its bubbles, and you can measure directly how much CO2 and methane were in the air when mammoths walked across a frozen Europe. For the first time, climate scientists had not just a record of how cold it was, or how much ice there was, but what the atmosphere itself had looked like through multiple glacial cycles. When those gas measurements were plotted against the isotope-based temperature proxies, the result was quietly astonishing. Across hundreds of thousands of years, CO2 and methane rose and fell in step with the glacial rhythm. During full glacials, when delta the Hempf-et-O in the oceans was high and ice sheets sprawled over continents, CO2 was low, around 180 to 200 parts per million. Methane, a powerful but short-lived greenhouse gas, was low as well. As the planet warmed into an interglacial, like the one we live in now, both gases climbed. CO2 rose toward 260, 280, sometimes a bit higher. Methane roughly doubled. The temperature proxies in the ice moved with them, and the marine Delta 8O record showed ice sheets shrinking back toward the poles. The timing was delicate. In most cases, the onset of warming seemed to begin with orbital changes and subtle shifts in sunlight distribution, especially at high northern latitudes. Temperatures started to tick upward. Then greenhouse gases increased, amplifying the initial nudge. The ice cores suggested that CO2 and methane were not the metronome itself, but they were certainly the volume dial. Crucially, the ice records also revealed something the deep sea cores had mostly smoothed away: abruptness, layer by layer. Greenland in particular showed episodes where regional temperatures jumped by several degrees in just a few decades. These so-called Dansgaard-Eschger events punctuated the last glacial period with sudden warmings and more gradual coolings, like a heartbeat superimposed on the slower orbital swing. Methane spikes often accompanied these events, likely reflecting rapid changes in tropical wetlands. Dust levels shifted as storm tracks reorganized in Antarctica. The same period showed more muted but still noticeable changes, offset in time by the slow pulsing of ocean circulation between the hemispheres. Set beside the slow 2341 and 100,000-year orbital pacing inferred from the oceans, the ice cores told a more complicated story. Climate did not simply slide gently from one state to another. It could lurch, snap, and rearrange itself on timescales that mattered to individual human lifetimes, all while still respecting the longer rhythm imposed by planetary geometry. The ice also helped calibrate and test the astronomical theories. Where the deep-sea record had dating uncertainties of thousands of years, annual layers in the upper parts of ice cores anchored specific events more precisely. Volcanic ash layers that appeared in both ocean mud and polar ice linked the two archives together. Changes in atmospheric methane traced in the bubbles could be matched to signals in tropical sediments. Yet for all their clarity, the ice cores had their own limitations. They are by nature polar records. Their temperature proxies reflect conditions over Greenland or Antarctica, not necessarily the tropics or mid-latitudes where much of the action of monsoons, forests, and early humans played out. Local weather patterns, changes in storm tracks, and shifts in sea ice extent can all influence what the isotopes record at a given site. Even the age of the gas bubbles is slightly offset from the age of the ice around them. It takes decades to centuries for snow to compress enough to seal the air, so a bubble trapped at, say, 2,000 meters depth might be 100 or more years younger than the ice crystal enclosing it. Correcting for that so-called gas age, ice age difference adds uncertainty, especially deeper in the cores. And while ice cores resolve rapid changes beautifully for the last glacial cycle or two, their resolution blurs further back. Over hundreds of thousands of years, thinning and deformation of the deep ice smear short-lived events together, much as sedimentation does in the oceans. No single archive by itself can answer every question. The oceans are superb at recording global ice volume and slow, integrated changes in climate, but they struggle with abrupt transitions. Ice cores capture atmospheric composition and fast swings, but only from the ends of the Earth, and only for the last few glacial interglacial cycles in high detail. To understand why Earth's ice ages shifted from a 41,000-year pattern to the puzzling 100,000-year beat, and how carbon dioxide interacted with that shift, scientists had to weave these archives together: mud from the seafloor, bubbles from the ice, dust from ancient deserts, fossils from lake beds. Only by listening to all of them at once could they begin to hear the full harmony: orbital cycles setting the key, greenhouse gases shaping the melody, and the oceans and ice sheets providing the slow, powerful bass line of the Pleistocene world. If you roll the tape of Earth's climate backward from the present, through the last few glacial cycles the ice cores describe so clearly, something curious happens. For a while the rhythm looks familiar: big peaks and valleys, ice sheets growing and shrinking on a roughly 100,000-year schedule. Then, somewhere between about 800 and a million years ago, the pattern begins to soften and blur. The huge swings in global ice volume shrink. The deepest glacials are not as cold, not as icy. The spacing between major warm periods tightens. Push back further into the early Pleistocene and the end of the Pliocene, and the beat of the climate system is cleaner, almost metronomic. About every 41,000 years the planet breathes. This was the obliquity world, a time when Earth's tilt relative to its orbit was the main drummer for the ice ages. Today, Earth's axis is tilted at about 23.5 degrees. Over tens of thousands of years, that tilt slowly rocks back and forth between about 22 and 24.5 degrees. It's a gentle wobble, but it has powerful consequences. A greater tilt means the poles lean more strongly toward and away from the sun over the course of a year. Summers at high latitudes become a little brighter, winters a little darker. The total amount of sunlight reaching Earth over a year doesn't change much. What changes is where and when it arrives. In the early Pleistocene, the climate system seemed to respond to this 41,000-year tilt cycle with impressive obedience. When the tilt was high, polar summers were stronger. Ice that had accumulated on northern continents melted back more easily. Sea ice retreated. The great conveyor belts of ocean circulation shifted toward a warmer mode. Greenhouse gases rose, amplifying the warming, and the world moved into an interglacial. When the tilt relaxed and summers at high latitudes weakened, snow that fell one winter was more likely to survive the following summer. Year after year, that surviving snow could build into glacial ice. The reflective, high albedo surface of expanding ice sheets bounced more sunlight back to space. Oceans cooled and stored more carbon. Greenhouse gases fell. The planet tipped back toward a glacial state. On the seafloor, this orderly breathing is recorded as a regular sawtooth in the Delton-Waititi curves. During the early Pleistocene, those curves show relatively modest swings that line up neatly with the 41,000-year tilt cycle. When researchers run spectral analyses, mathematical tools that decompose a signal into its underlying frequencies, the obliquity peak dominates. The 100,000-year component that looms so large later is faint, almost an afterthought. Part of the reason lies in the geometry of the continents and the size of the ice sheets themselves. In that earlier world, large northern hemisphere ice sheets certainly existed, but they were smaller, shallower, and more short-lived than the massive domes that would come later. They tended not to grind their way so far south into mid-latitudes. They sat more squarely under the part of the sky most sensitive to tilt. With less ice volume piled on the continents, the bedrock beneath them had not yet been pushed down as deeply. The shape of the land under the ice was different. Coastlines and continental shelves were arranged in slightly other ways. The so-called boundary conditions, the background geography and ocean atmosphere configuration on which the climate system operates, were not identical to those of the late Pleistocene. Smaller ice sheets also mean less inertia. A compact glacier sitting atop a relatively unwarped landscape can adjust more quickly to changes in summer sunlight. If high-latitude insolation drops for a few thousand years, its edge can advance. If summers strengthen, it can retreat. It is like a small, nimble boat responding to the push of a modest wave. Under those conditions, the direct link between obliquity and ice is easier to maintain. The climate system can track the slow rocking of Earth's tilt without getting stuck. The early Pleistocene ocean helped enforce this discipline. With limited continental ice volume, sea level was higher on average. Shallow continental shelves that would later be exposed as dry land remained submerged. Ocean basins were less isolated from one another by emergent land bridges and ice dams. Circulation patterns appear to have been somewhat more stable. The deep ocean could exchange carbon with the atmosphere and upper layers on timescales that, while still slow by human standards, were fast enough to keep pace with the 41,000-year rhythm. When tilt increased and high-latitude oceans warmed, carbon dioxide would tend to leak out of the deep, reinforcing the warming. When tilt decreased and northern waters cooled, more carbon could be drawn down and stored. In this mode, obliquity is enough. Change the tilt, and the whole coupled system, ice sheets, oceans, atmosphere and carbon cycle, shifts with it in relatively smooth 41,000-year swings. Yet even within this apparently tidy regime, hints of change were accumulating. If you line up stacks of deep-sea cores that span the last few million years and look carefully, you can see it. Around 1.5 million years ago, the glacial cycles are indeed shorter and shallower. The amplitude of delta 30O variations is modest, but moving toward 1.2 million, 1.0 million, 0.8 million years ago, the troughs deepen. The glacials grow a bit colder, a bit icier, a bit longer. The 41,000-year pacing remains visible, but some glacials begin to skip a beat. Instead of fully melting back with every obliquity maximum, ice sheets in some cycles linger. They partially survive through one high tilt interval and only retreat dramatically after 2 or even 3 obliquity swings have passed. This is the gradual drift toward a more reluctant, more hysteretic climate, one with memory. As ice sheets grew larger in certain cycles, they altered the very conditions that had once made them so responsive. Their weight depressed the continents more deeply, changing surface elevation, regional climate, and patterns of ice flow. Their expanding white surfaces cooled the air above them and deflected storm tracks. As they pushed farther south, they covered land that received more sunlight, increasing their leverage over the planet's energy balance. The oceans, too, began to feel the difference. Larger ice sheets meant lower global sea level, exposing continental shelves and constricting shallow seaways. This changed how water masses could move between basins. It modified where deep waters formed, how nutrients were cycled, how easily the deep ocean could trade carbon with the atmosphere. In climate models and in geologic proxies, there are signs that the deep ocean began to store more carbon during these deeper glacials. Keeping atmospheric CO2 lower for longer, that extra carbon storage would make it harder for a single 41,000-year tilt maximum to kick the system fully out of a glacial. The climate system was slowly arming a kind of internal resistance. By the time we reached the interval between about 1.2 and 0.8 million years ago, this slow drift has prepared the stage for something new. The tilt cycle has not gone away. Earth's obliquity continues to rock back and forth on schedule. But the planet's response is changing. Ice sheets are large enough, and the oceans reconfigured enough, that their own feedbacks begin to rival the direct influence of tilt. The deep-sea records show it first. Glacials stretch out. Some interglacials are weak or missing, over tens and then hundreds of thousands of years. The power in the 41,000-year band of the delta et O spectrum begins to wane, while a new, stronger rhythm emerges on timescales closer to 80 to 120,000 years. Nothing in Earth's orbital geometry suddenly adds a brand new 100,000-year cycle strong enough to explain this on its own. eccentricity, the shape of the orbit, does vary on roughly that period, but its direct effect on sunlight is small compared to tilt. This is the core of the mystery that drew climate scientists into those ice cores and sediments in the first place. For more than 1,000,000 years, the planet's ice had breathed in time with the slow nodding of its axis, inhaling and exhaling on a 41,000-year beat. Then, over a relatively brief geological interval, the rhythm changed. Glacials became fewer but deeper, interglacials more widely spaced. Somehow, the climate system learned to count differently, emphasizing a faint 100,000-year orbital whisper and subordinating the once dominant tilt cycle. How and why that switch happened, the so-called mid-pleistocene transition, is one of the most intriguing puzzles in the story of Earth's ice ages, and it is where the pattern that would shape human history truly took form. From the point of view of the sediments, the mid-Pleistocene transition is not a single line on a graph, not a cliff you can stand on and look over the edge. It is more like walking through fog and realizing, several hours later, that the landscape around you has changed. Between about 1.2 million and 700,000 years ago, the climate system passes through that fog. If you stack the Delta 18 records and line them up carefully, you can watch the shift unfold. Early in this interval, the 41,000-year pulses of obliquity are still clearly there. Each peak and trough in Earth's tilt leaves an echo in global ice volume. But the echoes are getting distorted. Some glacials deepen far beyond their predecessors. Others refuse to let go. Interglacials that would once have been vigorous thaws turn into muted warmings, barely lifting global ice volume above its glacial baseline before the system slides back into cold. By around 900,000 years ago, the pattern looks different again. Full deglaciations are rare. Instead of springing back after every tilt maximum, the ice system sometimes waits through 2 or 3, building up ice through successive cool summers and only collapsing in a truly massive melt after a long, drawn-out glacial. The average length of a glacial-interglacial cycle stretches. What had been a rhythm of roughly 41,000 years slowly drifts towards something closer to 80, then 100, then 120,000 years between major warm peaks. At the same time, the ice sheets themselves are changing character. In the early Pleistocene, northern ice sheets were big by human standards, but in geological context they were tentative. They advanced and retreated like a tide lapping at the edge of a beach, rarely pushing far into the heart of the continents. Through the mid-Pleistocene, they begin to behave more like a dammed reservoir. Each cold phase allows more snow to survive summer. Each extra winter adds another thin layer of ice. Under their growing weight, the continents flex downward. Valleys deepen, basins form. The ice finds new ways to flow, new channels that funnel it south into lower, sunnier latitudes, where once established, it reflects even more sunlight back to space. With more volume and a broader footprint, these ice sheets have more inertia. They no longer melt away at the first sign of a strong summer. A single obliquity maximum is often not enough. You may need 2 or 3 favourable tilt cycles, lined up with helpful precession and modest eccentricity, to overcome the accumulated cold. From the perspective of the climate system, this is a phase change in personality. The old obliquity-dominated world was twitchy and responsive. The new one is stubborn and delayed. It takes longer to build ice, longer to melt it, and the extremes on both ends are greater. Glacials are colder and longer. Interglacials, when they arrive, are sharper events erupting from a deeper background of ice. Why this happened is where the arguments begin, and where some of the most creative work in paleoclimate has focused. One influential idea is the regolith removal hypothesis. Regolith is the loose blanket of soil, gravel and weathered rock that normally covers continental surfaces. Early in the Pleistocene, northern ice sheets, mostly sat on this soft, deformable layer. Like a heavy sled on wet sand, they could slide relatively easily, keeping their thickness limited. They spread out, but they did not pile up into towering domes. Over hundreds of thousands of years, those ice sheets acted like giant bulldozers. They scraped away the regolith, planed surfaces down to hard crystalline bedrock, and flushed the debris into the oceans. As more of the northern continents were stripped, later ice sheets began to sit on this exposed, rougher foundation. Ice resting on hard bedrock behaves differently. It tends to lock in place and thicken rather than slide outward. That makes it easier to accumulate large volumes of ice, which in turn amplifies the feedbacks that favour long glacials. Higher albedo, colder regional climates, stronger impacts on atmospheric circulation. In this view, the mid-pleistocene transition is the moment when enough regolith had been removed that the mechanical rules of glaciation changed. The ice sheets, in effect, discovered a new mode fewer, fatter glacials paced, not simply by tilt, but by their own evolving geometry. Another family of explanations focuses on internal ice sheet dynamics. Even without changing the bed beneath them, large ice sheets are nonlinear systems. They can have multiple stable states, a small configuration that tracks summer sunlight closely, and a massive configuration that persists until some threshold is crossed. In models of this kind, as the climate gradually cools over the Pleistocene, for reasons tied to slow tectonic changes, long-term CO2 decline, and shifting ocean gateways, the system moves closer to that second state. At some point in the mid-Pleistocene, the ice sheets become just big enough, and the background climate just cold enough that they begin to get stuck in the large ice configuration. Interglacials then require a rare coincidence of orbital factors plus internal instabilities, ice streams accelerating, ice shelves collapsing, feedbacks in surface melt and albedo to knock the system back into a warm phase. The spacing of those big collapses naturally falls into the longer, roughly 100,000-year band where eccentricity modulates the strength of summers. There are also hypotheses that put the oceans at centre stage. As the ice sheets grow and sea level falls, shallow seas retreat from continental shelves. Narrow passages between ocean basins become choked or exposed. The pattern of where dense waters form and sink into the abyss shifts. With it, the deep ocean's ability to exchange carbon with the atmosphere changes. Some models suggest that during the mid-Pleistocene, the deep ocean gradually became more efficient at hoarding carbon during glacials. Colder waters, altered circulation routes, and expanded sea ice might all have contributed. The result would be lower atmospheric CO2 for longer periods, reinforcing the cold and making it harder for a single tilt maximum to trigger a full deglaciation. In this framework, the transition is a reorganization of the global carbon climate system. Ice sheets, oceans and atmosphere settling into a new pattern of long, CO2-suppressed glacials separated by briefer, high CO2 interglacials. None of these ideas is entirely sufficient on its own, and none has been universally accepted. Regolith removal explains the increasing size and stability of ice sheets, but it is difficult to test directly, because the best evidence, those scraped clean continental surfaces, has itself been erased and reworked many times. Ice sheet dynamical models can reproduce 100,000-year like cycles, but they depend sensitively on parameter choices, how easily ice flows, how it melts at the margins, how it interacts with the bed and the ocean. Ocean circulation and carbon cycle theories are grounded in proxies, chemical traces in shells that hint at past currents and CO2 levels, but those records are patchy and sometimes contradictory. Different cores tell slightly different stories. What most researchers do agree on is that the mid-Pleistocene transition was not caused by any sudden change in Earth's orbit. The astronomical forcing remained the same, slow, predictable combination of tilt, precession and eccentricity. The shift came from inside the climate system. Over many 41,000-year cycles, incremental changes accumulated, continents eroded and flexed, regolith was stripped, sea level ratcheted down and up, ocean gateways narrowed, the long-term carbon balance drifted. Piece by piece, these alterations changed how the planet could respond to the familiar orbital nudges. By roughly 700,000 years ago, the transformation is mostly complete. The spectral fingerprints in the sediment record show a world in which the 100,000-year rhythm dominates, even though the direct 100,000-year orbital signal remains weak. The old obliquity-paced mode has not vanished, its imprint is still visible in the fine structure of each cycle, but it has been wrapped inside a slower, heavier envelope defined by the growth and collapse of truly massive ice sheets. This is the new Ice Age world, the one with deep, drawn-out glacials and rare, precious interglacials like the one we live in now. And while no human eyes were there to see the switch, this is the climate backdrop against which our own lineage was being hammered into shape. From a purely astronomical point of view, this new rhythm is strange. If you rank the three main orbital cycles by how strongly they change incoming sunlight, eccentricity comes last. Tilt reshapes the contrast between seasons, especially at high latitudes. Precession, swinging the timing of perihelion around the calendar, can turn a northern summer into a brief distant sun affair, or a long, close sun one. Both have clear, immediate consequences for whether winter snow in Canada or Scandinavia survives the following summer. Eccentricity, by contrast, mostly just changes how slightly oval Earth's orbit is. The total annual sunlight barely shifts. Even the seasonal effects are subtle, working mainly by modulating how strongly precession matters. When the orbit is more eccentric, precession has teeth. When the orbit is nearly circular, precession's impact on seasonal contrast is gentler. On paper, it looks like the supporting character, and yet, in the late Pleistocene, the big swings in ice and climate line up most strongly with this 100,000-year beat in eccentricity. This mismatch is what climatologists call the 100,000-year problem. If you plot the raw astronomical forcing and then plot the global ice volume inferred from oxygen isotopes, the tall peaks in ice, those deep glacials that end in dramatic terminations tend to cluster around times when eccentricity is relatively high, giving precession a bit more leverage. But the amplitude of that orbital change is tiny compared to the sheer size of the climate response. It is as if you whisper every 100,000 years, and the ice sheets sometimes answer with a shout. This tells you immediately that the climate system is not behaving like a simple linear amplifier. It is not just taking the incoming sunlight signal and scaling it up or down in a neat, proportional way. Something more complicated is happening, something that stores history, accumulates tension, and then releases it in jumps. In the language of physics, this is threshold behavior. Imagine a balance scale with a slowly growing stack of weights on one side. Each individual weight is small, almost insignificant. For a long time, the scale hardly moves. Then, at some point, one more tiny weight tips it, and the whole system snaps to a new position. Late Pleistocene ice sheets look more and more like that kind of system. As the background climate cooled and the northern continents were reshaped by repeated glaciations, summers that were just a little bit weak, thanks to a particular combination of tilt and precession, could allow more snow to survive than melt. That extra snow thickened the ice, which cooled the region, which allowed more snow to survive the following year. An accumulation of small advantages. The system does not need a single huge orbital push to build massive ice. It just needs enough consecutive mildly favourable summers, stacked one on top of another, to creep up on a threshold. The puzzle, then, is why the big deglaciations, the times when the system finally crashes back into warmth, are organised into that 100,000-year band. One way to think about it is in terms of skipped beats. In the early Pleistocene, when ice sheets were smaller and the climate more responsive, nearly every strong tilt maximum could, in principle, trigger a substantial retreat. The system's natural rhythm matched the 41,000-year obliquity cycle. In the late Pleistocene, with thicker, more inert ice sheets and deeper glacials, a single favourable tilt peak was often not enough. The system began to ignore some of the beats it once followed. You might go through one tilt maximum with only a modest thinning of ice. The threshold is lower, but still not reached. Then another with a bit more retreat, but still no collapse. With each skipped beat, the system's internal state changes: ice geometry, bedrock depression, sea level, CO2, ocean circulation. Instabilities build quietly. By the time 2 or 3 obliquity cycles have passed without a full deglaciation, the system is primed. Ice sheets have spread outward, grounding lines have advanced across widened continental shelves, sea level is low, the deep ocean is packed with carbon. Under these loaded conditions, the next time orbital geometry lines up just right, tilt high, precession timing favourable, eccentricity giving precession that extra edge, the response is no longer incremental. The scale tips, the dam breaks. From the outside, looking only at the sediment record, it appears as though the climate has started to follow a 100,000-year metronome. From the inside, it may be more like a pattern of accumulated stress and delayed release, whose average spacing naturally gravitates toward the slow envelope, within which many tilt and precession cycles play out. Climate models that try to reproduce this behavior have to walk a narrow path. If you give the system too much inertia, it hardly responds at all. Ice sheets grow and stay grown, shrugging off even the strongest orbital nudges. If you make it too sensitive, it flips back and forth with every small change in summer sunlight, tracking obliquity almost perfectly and never building the long, deep glacials we observe. To get something like the real late Pleistocene modelers introduced nonlinearities, thresholds for rapid ice sheet collapse, when grounding lines retreat from continental shelves, feedbacks in albedo when melt ponds and bare ice appear, changes in basal sliding when pressure and meltwater reach certain limits, couplings to the carbon cycle that allow CO2 to slowly fall during glacials and then surge back at terminations. When these ingredients are tuned within plausible ranges, some models begin to generate self-organized 100,000-year cycles. They do not impose a 100,000-year orbital forcing directly. They simply feed in the known tilt and precession changes, plus the gentle modulation from eccentricity, and let the ice sheets and oceans decide when to jump. In such simulations, you often see skipped beats. A sequence of obliquity peaks passes with only partial retreats, because the internal state of the ice-ocean carbon system has not yet reached the critical configuration. Then suddenly a modest extra push, slightly higher eccentricity, a fortunate precession phase, or a particular configuration of ocean circulation crosses the invisible line, and a full termination unfolds. Even then, the timing is not perfectly regular. Some simulated cycles last 80,000 years, some 120. The 100,000-year band is a statistical tendency, not a rigid clock. That, too, matches the geological record. The 100,000-year problem remains a problem because no model yet captures all the features of the cycles for all the right physical reasons. Different researchers emphasize different pieces: ice sheet mechanics, regolith, CO2, ocean stratification, sea ice extent. Each can generate 100,000-year like pacing under certain assumptions. But what almost everyone agrees on is the core lesson. The late Pleistocene climate system is not a passive mirror of orbital forcing. It is an active, memory-bearing, non-linear player, capable of turning small, regular celestial nudges into irregular, massive reorganizations of ice, ocean, and atmosphere. And those reorganizations, those rare warm interludes between long glacials, are the stages on which our own story has unfolded. To understand why those reorganizations are so dramatic, you have to zoom in on the ice itself. Not the abstract ice volume curve on a graph, but the real physical thing, blindingly white sheets of frozen water spreading across continents kilometers thick, altering everything around them. The first big trick ice plays on climate is albedo. Albedo is just a measure of reflectivity. Dark ocean water absorbs most of the sunlight that hits it. Forests and bare rock absorb a lot too, turning that light into heat. Fresh snow and clean glacier ice, by contrast, bounce most of that sunlight straight back into space. So the moment snow starts to linger through the summer in high latitudes, the local surface goes from relatively dark to dazzlingly bright. The same amount of sunlight arrives from the sun, but far less of it gets stored as heat at the surface. Temperatures drop a little. That extra bit of cold lets more snow survive the next summer, which makes the surface even brighter, which cools things further. This is a feedback loop. The initial push might be tiny, a slightly weaker summer thanks to an unlucky combination of tilt and precession, or a bit more sea ice chewing up open water. But once snow cover crosses a certain persistence threshold, staying long enough into summer that vegetation dies back and bare ground stops reappearing, the albedo feedback kicks in. You can think of it like painting the planet, stroke by stroke, with a more reflective colour. Every patch you paint makes it easier to paint the next patch. As ice sheets grow, another feedback joins in: height. Air cools as it rises roughly 6 or 7 degrees Celsius for every kilometre under typical conditions. Build an ice sheet high enough, and you are literally lifting the surface of the Earth into colder air. Early in a glaciation, when ice is still thin, its main role is reflectivity. But as it thickens into a true continental sheet, hundreds, then thousands of meters, its top surface climbs. The summit of the Laurentide ice sheet over North America at its peak may have stood more than 3 kilometers above sea level. The East Antarctic ice sheet today reaches even higher. Up there, summers are not just slightly cooler. They can be fundamentally unable to melt away the winter snow, even during otherwise warm orbital phases. The ice has created its own little high-altitude world, perched in the mid-troposphere, decoupled from the milder climate at sea level. This elevation temperature feedback makes big ice sheets stubborn. Once they are tall enough, they help preserve themselves. But nature rarely gives us simple, one-directional stories. As ice expands, new processes appear that tug against these runaway tendencies, or complicate them. One of the most important is dust. Glacial periods are dusty times. With more of the world's water locked up on land, sea levels fall and large areas of continental shelf are exposed as bare, wind-scoured plains. Colder, drier climates weaken vegetation, leaving soils loose. Stronger winds, driven by steeper temperature gradients between equator and pole, pick up that dust and carry it across the globe. Some of it falls on ocean surfaces, fertilizing plankton. Some settles on distant continents, and a lot lands on the ice itself. Fresh snow has an albedo so high, it almost hurts to look at under bright sun. Sprinkle it with enough dark particles, dust, soot, fragments of rock, and that reflectivity drops. The snow absorbs more sunlight, warms up, and melts more easily. This snow darkening effect is a kind of hidden brake on ice growth, and an accelerator of melt once conditions swing warm. In late stages of glacials, when the world is especially dusty, a feedback can emerge. More ice cover exposes more barren, dusty ground, which coats more of the ice, which makes it more vulnerable when orbital forcing starts to favour melt. On a sunny, late glacial day, the meltwater can organise itself into a complex network of streams, ponds, and buried channels. Where water pools, the surface darkens further, creating melt ponds that absorb even more solar energy, drilling down into the ice. At the base of all this, out of sight, other feedbacks are operating. Ice sheets are not rigid, crystalline blocks. Under their own immense weight, ice deforms and flows. Where it meets the underlying rock, the behaviour of that contact zone, cold and frozen, or lubricated by water and sediment, has enormous influence on whether the sheet sits still or starts to slide. If the bedrock is rough and firmly frozen to the ice, friction is high. The ice moves slowly, if at all. That helps it stay piled up on land, anchoring the sheet. Introduce liquid water at the base, though, and everything changes. Pressure from the overlying ice can melt a thin film at the bottom even when temperatures are below zero. Geothermal heat from Earth's interior contributes, especially where the crust is thinner. Surface meltwater can also find its way down through crevasses and moulins, delivering warmth and fresh water directly to the base. When enough water accumulates, it acts like grease between the ice and the bed. Patches of the sheet can suddenly speed up, sliding toward the ocean. Whole ice streams, fast-flowing rivers of ice, tens of kilometers wide, can form, draining the interior. The nature of the bedrock matters too. In some regions, especially early in the Pleistocene, thick layers of loose weathered sediment called regolith covered the continents. Ice sitting on this soft material could deform it easily, spreading out and sliding relatively smoothly. Over many glacial cycles, repeated passage of ice scraped that regolith away, exposing harder, more irregular bedrock. This may have made later ice sheets more prone to locking in place, building up great thickness, and then releasing catastrophically when basal conditions finally tip toward sliding. So you have albedo trying to keep things cold and white, elevation making tall ice self-sustaining, dust and darkening undercutting reflectivity, basal water and bedrock sometimes locking the sheets down, sometimes sending them surging toward the sea. These are not gentle, linear responses. They are switches. A little bit more snow might not matter, until it pushes the surface high enough to stay frozen through summer. A little bit more dust might not show, until it crosses the line where melt ponds form everywhere. A slow trickle of basal water might do nothing, until it links up into a pressurized layer, and the ice above suddenly lurches forward. When you stack all of these feedbacks together, you get a system that remembers its past and reacts in bursts. Orbital changes provide a steady, predictable rhythm in incoming sunlight. But ice, with its bright surfaces, towering heights, dusty skins and slippery beds, turns that smooth rhythm into something jagged. It can ignore a series of favourable summers, holding on stubbornly. Then, when thresholds are crossed, when albedo, elevation, darkening, and sliding line up, just so it can respond with an outsized, cascading shift. That is how a planet can drift gradually into deeper and deeper glaciation, then, seemingly all at once, shed its ice sheets and leap into warmth. And under those leaps, hidden from view, another player is moving slowly, the ocean taking up and releasing heat and carbon, steering where and when the ice's runaway tendencies can actually unfold. If the ice sheets are the visible machinery of the ice ages, the oceans are the buried engine room. Almost all of the variable heat in the climate system lives in the ocean, not in the air. The atmosphere is thin, light, and fast-moving. It responds quickly to changes, whipping up storms, shifting jet streams, drying one region while flooding another. But in terms of sheer heat content, it is a skin. The upper few meters of the ocean contain more heat than the entire overlying atmosphere. And that is just the surface. Below it lies a vast, cold, dark reservoir stretching down thousands of meters, layered and stratified, moving on timescales that make human history look like a flicker. When we talk about glacial cycles, we're really talking about rearrangements of this enormous storehouse. On a day-to-day basis, the surface ocean interacts with the atmosphere, trading heat and moisture. Sunlight warms the top layer, winds and waves stir it, storms pull heat out. In summer, That mixed layer may reach 50 or 100 meters deep. Below it, temperatures plunge. In most of the deep ocean, from about 1,000 meters down to the seafloor, water hovers just above freezing, even in the tropics. So the question for ice ages is not just how much sunlight arrives from space, but how the ocean decides to connect or disconnect those layers. One way it does that is through the global conveyor belt of currents driven by differences in temperature and salinity, thermohaline circulation. In the modern world, this circulation has a recognizable pattern. Warm, salty surface water flows northward in the Atlantic, carried in part by the Gulf Stream. As it loses heat to the air and mixes with colder waters, it becomes denser. In the subpolar North Atlantic and around Greenland, some of it becomes dense enough to sink. That sinking helps pull more warm water northward, sustaining the flow. The water that dives down there does not come back to the surface for a very long time. It slides along the ocean floor, creeping south, then east into the Indian Ocean, then into the Pacific, gradually upwelling in scattered patches. Completing the loop takes on the order of 1,000 years. But that pattern is not fixed. It can weaken, strengthen, or even reorganize when the climate changes. During glacial periods, when vast ice sheets sit over North America and Eurasia, fresh meltwater pulses from ice margins can dilute the salty surface waters of the North Atlantic. Cooler air also changes the balance of heat exchange. These shifts can slow the sinking branch of the conveyor, redirecting where and how deep water forms. The evidence locked in ocean sediments, tiny shells of plankton that record temperature and chemistry, suggests that during many glacial intervals, deep water formation shifted southward and the Atlantic overturning weakened. The ocean became more two-story, a cold, isolated deep layer holding onto carbon and nutrients, and a thinner, more extreme surface layer reacting to the glacial winds above. That isolation matters, because the ocean is not just a heat reservoir. It is also the largest fast-changing carbon reservoir on Earth. Carbon dioxide moves readily between air and sea. Cold water dissolves more CO2, warm water releases it. Currents that bring deep water to the surface can burp out ancient carbon. Currents that submerge surface water can hide it away for a millennium. Nowhere is this more important than in the Southern Ocean, the ring of water encircling Antarctica. There the major oceans meet. Powerful westerly winds roar around the continent, unimpeded by land, driving a continuous eastward flow. In many regions, those winds pull surface water away from Antarctica, allowing deep water to well up from below to replace it. That upwelled water is special. It is old, centuries to millennia removed from the last time it touched the air. It is rich in nutrients because decaying plankton and sinking organic matter have been raining into the deep all that time. And it carries a high concentration of dissolved CO2. When that water reaches the surface, two things can happen. If the air above it is relatively low in CO2, the ocean will outgas, releasing carbon to the atmosphere. If conditions favour intense plankton growth, some of that carbon will be pulled into new life and eventually sent back downward as organic rain. Changes in Southern Ocean winds, sea ice cover, and mixing depth can tip the balance between those fates. Glacial climates seem to push the system towards storage. Colder surface waters and expanded sea ice limit the exposure of deep water to the air. Stronger stratification keeps the deepest, most carbon-rich layers from fully reaching the surface. Meanwhile, iron-bearing dust falling on those nutrient-rich waters may fertilize plankton blooms, helping lock more carbon into the deep. The result, more CO2 stays dissolved in the ocean, less lingers in the air. The atmosphere's greenhouse blanket thins. Temperatures drop further. Ice sheets find it easier to grow and persist. In this way, the ocean's slow respiration, the way it inhales carbon into the depths and exhales it back into the sky, becomes a quiet partner to the ice's more dramatic advances. Sea ice adds another twist. Unlike the giant land ice sheets, sea ice floats. It forms when the surface of the ocean itself freezes, spreading outward from polar coasts during long winters. A thin skin of sea ice is already quite reflective. Covered with snow, it can approach the albedo of a glacier. So expanding sea ice extends the bright shield over dark ocean water, helping cool the polar regions, reinforcing the temperature gradient between equator and pole, and strengthening the winds that drive ocean circulation. But sea ice does more than reflect sunlight. It acts as a lid. A solid ice cover cuts off direct contact between the atmosphere and the water below. Heat that would otherwise escape from relatively warm ocean to cold air is trapped. Gases, including CO2, have a harder time exchanging. Brine rejection, the process where forming ice expels salt, making the surrounding water denser, can drive local sinking and help ventilate certain depths, but the overall effect of a larger, longer-lasting sea ice cover is to insulate and compartmentalize the high-latitude ocean. This lid and shield behavior makes sea ice both a protection and a trap. In the growth phase of a glaciation, more sea ice helps the system cool, boosts the efficiency of carbon storage at high latitudes, and encourages the build-up of land ice. In the late stages of a glacial, when summer sunlight is gradually increasing, thanks to orbital shifts, that same sea ice can delay warming. The heat that is starting to accumulate in the atmosphere and mid-latitude oceans has to work harder for longer to break through the polar lid. But the longer it is delayed, the more energy collects in the system. This is where the hidden engine starts to shape the timing of glacial endings, the terminations. As orbital conditions slowly swing towards stronger high-latitude summers, sea ice retreats a bit farther each year. Southern ocean winds may shift slightly. The stratification that kept deep, carbon-rich water isolated begins to weaken in places. Patches of open water appear where, for tens of thousands of years, the surface had been capped. In those openings, deep water can finally reach the air in earnest. Upwelling intensifies, bringing old CO2-loaded water to the surface. Warmer air and reduced ice cover allow that CO2 to escape to the atmosphere. As atmospheric CO2 rises, it amplifies the direct solar warming, especially in winter and spring when sunlight alone is still modest. The ocean, which had spent the glacial storing cold and carbon, flips role. It becomes an accomplice in warming, as the Southern Ocean exhales and Atlantic overturning circulation reconfigures, the extra heat and greenhouse gas load spreads. Ice sheets experience warmer air, warmer ocean water lapping at their marine margins, and longer melt seasons. Meltwater pulses and ice sheet instability feed back into the ocean circulation, sometimes in sudden jumps. From the outside, it can look as if the climate has abruptly decided to abandon the glacial state. Within a geological blink, thousands of years, sometimes less, ice sheets that took tens of millennia to build shrink back, sea levels surge upward, and a relatively mild interglacial settles in. But under that apparent suddenness lies a long prelude, slow rearrangements of currents, gradual thickening and thinning of sea ice, subtle shifts in where waters sink and where they rise, the quiet filling and emptying of the deep carbon vault. The 100,000-year rhythm, in this view, is not just set by the geometry of Earth's orbit. It is paced by how quickly the ocean can be loaded with cold and carbon, how stable its stratification remains, and how abruptly that stability can be broken. Change the way the ocean breathes, and you change when the ice can truly let go. And every time the ocean has done that over the last million years, every time it has helped tear down an ice age and usher in a warm interval, it has been resetting the stage on which our ancestors would struggle, adapt, and eventually build the world we recognize. If the oceans are the engine room of the ice ages, carbon is the fuel that keeps changing what that engine can do. To understand why, you have to follow a single molecule of CO2 as it moves through the system. Imagine a molecule of carbon dioxide in the atmosphere during a warm interglacial. It drifts over the Southern Ocean and for a moment hits a patch of cold, choppy water. Cold water can hold more gas, so the ocean pulls that molecule down. It dissolves, joins a pool of dissolved inorganic carbon, and is carried into the interior by sinking currents. From there, the molecule might spend hundreds, even 1,000 years in the dark. It might get used by a deep-dwelling microbe, or simply ride along in a slow-moving current, waiting for the next chance to rise. Eventually, in some distant region of upwelling, it returns toward the surface. There, its fate branches. If it emerges into a world like ours with relatively high atmospheric CO2, it might stay dissolved. If the surface is cool and plankton are blooming, it might be taken up into new organic tissue, turned into a diatom shell or a tiny crustacean, then sink again in a biological snow. But in a different configuration of winds, ice and chemical balances, that same molecule could escape back to the air. And that choice, multiplied by trillions upon trillions of molecules over tens of thousands of years, is what shapes the carbon cycle's slow pulse. During glacial periods, more of those molecules end up staying in the ocean. Part of that is simple physics. Colder surface waters dissolve more CO2. As ice sheets grow and the planet cools, the average temperature of the surface ocean drops. That alone nudges the balance towards storage rather than release. But biology and chemistry pile on. In a glacial world, dusty winds scour the newly exposed continental shelves and dry steppe lands, lifting fine particles into the atmosphere. Ice cores show that glacial times are dusty times. A portion of that dust falls into the oceans, especially the Southern Ocean. That dust is not just dirt, it carries iron. Iron is a micronutrient that many ocean regions are starved of. The Southern Ocean is rich in nitrogen and phosphorus, but short on iron, which limits how much plankton can grow. When more iron falls from the sky, plankton can use more of the available nutrients. Blooms become more intense, more carbon is fixed into organic matter, and more of it sinks into the deep when those organisms die. This is the basis of the iron fertilization hypothesis, that glacial dust blown from cold, sparsely vegetated continents turned certain ocean regions into more efficient biological pumps. More carbon drawn out of the atmosphere, more buried in deep waters and sediments, less left in the air to trap heat. Weathering of rocks on land adds another piece. When rainwater, slightly acidic from dissolved CO2, runs over fresh rock surfaces, it slowly breaks down minerals. This chemical weathering consumes CO2 from the atmosphere and washes bicarbonate and other ions into rivers, which deliver them to the sea. There they contribute to the formation of carbonate shells and long-term carbon storage in sediments. On million-year timescales, weathering is one of the master controls of atmospheric CO2. But even on glacial-interglacial scales, shifts in ice cover, vegetation, and rainfall patterns can modulate it. Glaciers grind rock into fine flour. Retreating ice exposes fresh surfaces. Vegetation advances and retreats, changing how fast soils form and erode. The net effect is complex, and scientists still debate exactly how much of the glacial CO2 drop can be attributed to changes in weathering alone. It seems to be a background player, a slow, persistent sink, rather than the main driver of the 100,000-year rhythm. Then there are the frozen lands themselves. Permafrost, soil and sediment that stays frozen year-round, locks away immense stores of organic carbon. In cold, dry glacial climates, permafrost expands, pushing deeper into mid-latitude regions. Peatlands, tundra, and exposed continental shelves can all accumulate frozen carbon. At the same time, wetlands and shallow seas that, in warm periods, emit methane, are often reduced in extent. Methane hydrates, ice-like structures that trap methane in seafloor sediments, may be more stable in a colder ocean. These frozen and submerged reservoirs are smaller players compared to the deep ocean, but they matter because they are volatile. When they release carbon, especially methane, they can pack a strong short-term warming punch. When they grow, they quietly tighten the carbon budget. The ice core record hints at this delicacy. Methane concentrations swing dramatically between glacial and interglacial states, rising and falling in steps that often track monsoon strength, wetlands, and abrupt climate events. CO2 shifts are smoother, but even there, small kinks and pauses may record the breathing of these peripheral carbon pools. Put all of this together, and CO2 begins to look like both a follower and a leader. During the onset of a glaciation, orbital shifts start the process. Slightly weaker summers at high latitudes allow snow to linger, sea ice to expand. The planet cools. Colder water takes up more CO2. Enhanced stratification and changing winds in the Southern Ocean favour storage. Dustier air fertilises plankton. Frozen soils swallow carbon that once cycled quickly through plants and microbes. In this phase, CO2 is largely a feedback. It responds to an initial cooling driven by orbital geometry and ice albedo changes. But because carbon dioxide is such an efficient greenhouse gas, its response amplifies the original nudge. Lower CO2 makes winters harsher, summers shorter, ice more stable. What begins as a modest orbital suggestion becomes a locked-in glacial through the work of the carbon cycle. On the way out of a glaciation, the sequence reverses, but not perfectly. Orbital changes start pushing summers in the opposite direction. Sea ice thins and retreats. Winds and currents reorganize. The Southern Ocean's lid lifts in places, upwelling strengthens, deep carbon-rich water finally meets the air and begins to vent. Permafrost starts to thaw at the margins, releasing CO2 and methane. Vegetation spreads poleward, changing dust sources and sinks. Again, CO2 is initially a response, but once it starts to rise, it amplifies the warming, accelerating ice loss, changing rainfall, altering circulation in ways that further encourage the ocean to exhale. By the time an interglacial is established, atmospheric CO2 is both a memory of the deglaciation and a new starting condition for the next cycle. Untangling which came first, temperature changes, ocean rearrangements, or CO2 shifts, has become one of the central puzzles in paleoclimatology. Ice cores from Antarctica give us exquisitely detailed records of temperature proxies and trapped atmospheric gases. They suggest that, in many terminations, Antarctic temperatures begin to rise slightly before CO2 by a few hundred years. That points toward an initial orbital and regional ocean trigger, with CO2 following and then amplifying. But offshore in marine sediments, where tiny shells record deep ocean chemistry, the timing is less clear. Some records show hints that deep ocean carbon changes may begin early, perhaps even before the full Antarctic surface warming. Others suggest near synchrony within the uncertainties. Different regions tell slightly different stories. The Atlantic, Pacific, and Southern Ocean do not all move in lockstep. Their currents, stratification, and biology respond to the same orbital forcing on slightly different schedules. The carbon cycle's heartbeat is not a single sharp spike, but a blended sum of overlapping pulses. This is why even today scientists talk about partial mechanisms for the glacial CO2 drop. No single factor, temperature solubility, iron fertilization, weathering, permafrost, or ocean circulation, seems able to explain the full amplitude and timing on its own. Each contributes a piece. Together, they push the atmosphere from about 280 parts per million of CO2 in warm times down to roughly 180 in deep glacials. What is clear is that whenever that atmospheric number moves, the whole climate system leans with it. A few dozen parts per million of CO2, barely a chemical trace, help decide whether northern forests can grow where ice sheets once stood, whether rain falls on Saharan dunes or lush savannas, whether monsoon belts feed rivers or leave basins dry. For most of the last million years, these carbon swings have been slow, paced by dust, ice, ocean breathing, and rock weathering, acting over tens of thousands of years. Their rhythm set the background against which human evolution unfolded. And as that rhythm shifted from the older 41,000-year cycles to the newer 100,000-year beat, it didn't just change the timing of ice. It changed the length of the intervals in which our ancestors could thrive, migrate, and experiment with new ways of living. Those long CO2-shaped pauses between glacials became the windows in which our story could accelerate. For most animals, an ice age is just background. The winters are a little longer, the summers a little shorter, and life goes on until it doesn't. For our lineage, those swings were a kind of sculptor. Over the last million years, hominins never lived in a stable, unchanging world. Their ranges expanded and contracted like lungs with every glacial breath. Savanna became woodland. Woodland became scrub. Rivers shifted course. Lakes blossomed and vanished. What looked, from the slow perspective of ice sheets and ocean carbon, like smooth cycles, felt on the ground like endless surprise. In Africa, where much of our story played out, the continent didn't simply get wetter or drier in a smooth curve. It flickered. There were times when the Sahara, today one of the driest places on Earth, turned into a patchwork of lakes, marshes, and grassy plains. Green Sahara phases, driven by shifts in monsoons and orbital geometry, opened humid corridors from sub-Saharan Africa all the way to the Mediterranean. Hippos lived where there is only sand now. Crocodiles lounged in channels that are invisible except from space. Then, tens of thousands of years later, the rains would falter. Lakes shrank to salty puddles. Dunes marched across former shorelines. Those inviting corridors closed again, replaced by barriers of dust and heat. Farther south and east, the same rhythm played out in different keys. The East African rift, with its string of lakes and highlands, oscillated between wet phases with deep, interconnected basins and dry phases where many lakes nearly disappeared. Each configuration redrew the map of where food, water, and shelter could be found. For hominin groups living there, this wasn't an abstract climate curve. It was tomorrow's question: do we stay, or do we go? When lakes were full and grasslands broad, populations could spread, experiment with new hunting grounds, form links with neighbouring bands. When drought returned, those same landscapes became gauntlets. Groups that once exchanged mates and tools might find themselves separated by hundreds of kilometres of near desert. Others were squeezed together along the last reliable rivers, competing and cooperating in tense proximity. These shifting African wetlands and corridors may have been some of evolution's most efficient engines. Wet phases could connect distant populations, allowing genes and ideas to flow across the continent. Dry phases could isolate pockets of survivors in scattered refuges. Higher, cooler plateaus, forested river valleys, coastlines with reliable shellfish. Each refuge imposed its own demands and rewarded different skills. Over many cycles, this alternation between mixing and isolation would have encouraged both diversity and adaptability. Genetic studies of modern humans and our close relatives carry the echoes of this pattern. They point toward repeated episodes of population expansion and contraction, of fragmentation into regional groups, and later reconnection. Archaeology tells a parallel story. Tool styles that spread widely during favourable periods, then fragment into local traditions when environments turned harsh and travel routes closed. Ice didn't just press down on northern continents. It indirectly shaped where our ancestors could live, and how. At high latitudes, growing ice sheets and frigid winds drove many species south, compressing ecosystems into smaller belts. In Eurasia, hominins like Neanderthals and Denisovans found glacial refugia in mountain foothills, river valleys, and ice-free peninsulas. In these pockets cut off from one another for thousands of years, separate traditions could emerge. When the ice retreated just enough, those pockets reconnected. Populations met again, sometimes fighting, sometimes interbreeding, sometimes swapping technologies that had been invented in isolation. Something similar happened in the tropics without any need for local glaciers. Shifts in rainfall created their own refuges, gallery forests along rivers, coastal zones buffered by ocean humidity, upland regions where temperatures were milder and water more predictable. Hominins followed that mosaic, tracking the moving edges between too dry and too wet, too cold and too hot. Survival in such a world depended less on being perfectly tuned to one environment, and more on being able to cope with many. That is where technology and social organization start to matter. You can imagine two strategies. One is to evolve slowly toward extreme specialization, like an animal built precisely for dense rainforest or open tundra. The other is to lean into flexibility, tools that can be remade, shelters that can be improvised, social rules that can adjust to new neighbours and new threats. The fossil record suggests that our close cousins tried both paths. Neanderthals in Europe became extraordinary cold-weather hunters, with bodies and toolkits finely honed for glacial steppe and forest. Denisovans spread across an astonishing range of Asian environments, from tropical islands to high mountain plateaus, apparently mastering both boats and altitude. African populations that would eventually give rise to modern humans seem to have followed a different route, not specializing in one habitat, but learning to move between many. Unstable climates favored the second approach. If your food sources might shift by hundreds of kilometers over a few generations, it helps to have spears that can be redesigned for different prey. Fire-making techniques that work with whatever fuel is available, and social norms that allow strangers to be integrated into your group. It helps to be able to map your world in stories and memory, to remember that 3 days' walk east there is always water after the short rains, even if you haven't been there in years. We see hints of this in the archaeological record. During times of strong climate variability, more complex and diverse stone tool traditions, signs of long-distance movement of obsidian and other prized materials, ornaments and pigments that may have helped mark identity across larger social networks. These are the fingerprints of technological and social flexibility. But it is important to be careful with this story. Climate was not the author of human history, only a relentless editor. Shifts in rainfall and temperature set the stage, closed some doors, opened others. They created narrow windows when migration was possible, and long bottlenecks when only the best-placed refuges could sustain life. Within those constraints, though hominins chose, they learned, cooperated, fought, shared, and imagined. Different groups responded differently to the same pressures. Some failed and vanished, others found surprising solutions. The Ice Age rhythms did not dictate that our species would appear, or that it would eventually dominate the planet. But they did shape the landscape of possibilities. Which routes were open when, which resources were available, how long each relatively stable interglacial would last. Our ancestors lived inside those constraints for hundreds of thousands of years. Their minds, bodies, and cultures were tuned to a world that never sat still, to a climate that kept time with the slow ticking of Earth's orbit and the deep breathing of the oceans. And as those rhythms kept turning, the ice would do something else, something very simple and very profound. It would redraw the map. When people today look at a map of the world, it feels permanent. Continents, coastlines, oceans, all laid out like they've always been there. But for most of the last million years, those lines have been as temporary as footprints in wet sand. Every time the ice sheets grew, they locked up so much water that global sea level dropped by tens of meters, sometimes more than 100. The oceans shrank back from the land, and what we now think of as sea floor rose into the daylight. Continents didn't move very far in a geological sense, but to a walking primate, the difference between ocean and shallow shelf is the difference between impossible and Tuesday. Take the far north. During the height of many glacial periods, there was no Bering Strait as we know it. Instead, there was Beringia, a vast, cold, windswept land bridge connecting Siberia to Alaska. Not a narrow path, but a whole region the size of a small subcontinent, with rivers, grasslands, and herds of animals. That bridge likely appeared and disappeared multiple times over the last million years, tracking the slow seesaw of ice volume and sea level. When the ice swelled, sea level fell, and the bridge emerged, tying Asia and the Americas together. When the ice melted back, water flooded in and cut the continents apart again. Each time Beringia rose above the waves, it offered an invitation. Hominins and later modern humans could follow game and grasslands east, step by step, never needing to become sailors. Each time it drowned, that route snapped shut, and whatever life had crossed over was left to its own fate. Something similar unfolded in the tropics, but in a completely different climate. Look at Southeast Asia on a modern map, and you see a scatter of islands. Sumatra, Borneo, Java, hundreds of smaller pieces. During many glacial lows, those weren't islands. They were joined into a single great extension of the Asian mainland called Sunda. To the east, the continent of Australia and the island of New Guinea also sat higher above the ocean, forming a combined landmass known as Sahul. Between Sunda and Sahul lay a deep water trench that never fully drained, even when sea level was at its lowest. That gap, threaded by strong currents, is known as Wallessa. It was a chain of islands separated by channels that always required some kind of water crossing. Ice Age sea levels narrowed those channels and expanded the stepping stone islands. They didn't eliminate the barrier, but they made it far more negotiable for a species willing to experiment with rafts, dugout logs, or simple boats. At different times, Denisovans, Neanderthal cousins, and later modern humans seem to have pushed across those gaps, moving from a familiar Sunda world of tropical forests and river plains into the new, isolated ecosystems of Sahul, with its marsupials and giant birds. Without glacial sea level fall, that leap would have been orders of magnitude harder. The Mediterranean tells yet another version of the same story. Today, it feels like a broad, definite boundary between Africa and Europe, but the details have shifted with every cycle. During some glacials, sea level fell enough to widen coastlines and shorten crossings. Islands that are now remote stepping stones came much closer to their neighbours. Narrow straits, like the one between North Africa and southern Europe, shrank to their minimal width. We don't have perfect timelines for who crossed where and when, but the scattered evidence suggests that hominins repeatedly probed those edges. Stone tools on islands that were never fully connected hint at short sea voyages deep in the Pleistocene, long before anyone invented sails or maps. Lower seas and altered shorelines didn't just make the world smaller, they changed where curiosity could plausibly lead. And while sea level was opening some doors, ice and climate were slamming others shut. A glacial maximum was not simply colder everywhere. It was a radical reorganization of barriers and corridors. In Eurasia, enormous ice sheets pushed south, covering Scandinavia, much of Britain, large slabs of northern Germany and Russia. In front of these ice fronts, meltwater and grinding glaciers left behind moraines, outwash plains and unstable swampy ground. Whole regions became dead zones for hominin travel, too icy, too barren, or too dangerous to cross. Farther south, belts of steppe and semi-desert expanded. The great mid-latitude deserts of Asia, like the Gobi and Taklamakan, pulsed outward under glacial winds. The Sahara, when monsoons weakened, hardened into an almost continuous barrier of rock and sand. Mountain passes that had once been mild became sealed with year-round snow and ice. Routes that had linked populations during warmer intervals, river valleys, lowland forests, coastal paths were pinched off. Groups that once had neighbours just over the ridge suddenly found nothing but ice or dust. Then, as the planet eased back toward an interglacial, those same barriers softened. Ice fronts retreated uphill and northward, uncovering new plains and river systems fed by glacial melt. Permafrost thawed, deserts drew back as rainfall patterns shifted. The Sahara greened in pulses, suturing Africa back together with lakes and rivers. In Eurasia, formerly frozen corridors through mountain ranges and along coasts reopened, sometimes for only a few thousand years at a time. You can think of it as a slow planetary breathing, glacials tightening the arteries of movement, interglacials relaxing them. When the world tightened, isolation increased. Populations sat in refuges, developing local habits, dialects, technologies, even genetic quirks. When the world relaxed, those pockets met again. They exchanged mates, tools, stories, pathogens. Sometimes they fought, sometimes they blended so thoroughly that from our perspective the boundaries dissolve. These cycles didn't just guide where humans could go. They helped decide when the crucial journeys were even possible. The first movements of hominins into Europe, the spread of Denisovan-like peoples across Asia, the eventual leap of modern humans into Australia and the Americas, all of them seemed to coincide with windows when the map was temporarily favourable. Seas lowered, corridors damp instead of desiccated, ice walls pulled back just enough. And as you follow those ancient paths in your mind, it's worth remembering that our reconstruction of this shifting world is still a work in progress. New cores from the ocean floor, new cave sites on old shorelines, and new genetic studies are constantly refining the picture. If you ever want to drift deeper into that picture, into the ways climate, ice, and human stories weave together, there's a whole book of these long-form bedtime histories waiting at sleepytimehistory.com, and for this week, it's actually discounted. For now, though, just hold on to this idea. The map of the world your ancestors knew was not a single image, but a flickering slideshow. Coasts came and went, islands fused and separated. Deserts and forests traded places. Bridges of land rose out of the sea, and then vanished beneath it again. Every one of those slow, quiet changes set the options for the people living through them. Stay put in a shrinking refuge, or follow a new river. Wait out the dry years, or gamble on a corridor that has just reopened after 10,000 seasons of being closed. By the time the last great cycle rolled around, the one we often call the last ice age, our species had learned to read that moving map better than any of its cousins. And it was in that final swing from deep glacial cold to the mild climate we inhabit now that the edge of what we usually call history finally came into view. The last glacial cycle, the one that leads directly to us, begins around 120,000 years ago. Imagine hitting play on the climate record from that point. At the start, the world is already in a relatively warm phase, something like today. Ice sheets are smaller, forests reach farther north, coastlines are roughly where we'd recognize them. In Europe, early modern humans and Neanderthals are both present. In Africa, our own species is scattered in multiple regions using increasingly complex tools and social networks. In Asia, Denisovan-like populations still occupy vast territories. This is a brief high point in the 100,000-year rhythm, a crest before the long slide. Over the next tens of thousands of years, the orbital settings shift. Northern summers slowly weaken. Snow that falls at high latitudes is less likely to melt away completely. Glaciers inch outward year after year, millennium after millennium. Sea level begins to fall at first by just a few meters, then by dozens. To people living through it, there is no single day when the Ice Age begins. It's felt in small ways that accumulate. Winters that bite a little harder, animals shifting their ranges, plant communities rearranging. Local climates flicker back and forth, but the long trend is downward. By about 70,000 years ago, the planet is solidly on the glacial track. Ice sheets are expanding, deserts like the Sahara are often larger and drier, and many human populations are squeezed into refuges, some in Africa's wetter belts and coasts, some along Eurasian rivers, some on the exposed shelves of what we now call Beringia and Sunda. For a long time, people imagined this descent into the last glacial maximum as a smooth, slow ramp. Colder, then coldest, and then a gentle warming back out. The real story the ice cores tell is very different. When scientists drilled deep into the Greenland ice sheet and measured tiny bubbles of ancient air trapped in the layers, they found temperature records that looked less like a ramp and more like a seismograph. Jagged jumps, violent swings, sudden spikes of warmth erupting out of the cold background, then crashing back down again. These are the Dansgaard-Eschger events. Roughly every few thousand years during the last glacial, especially between about 90,000 and 30,000 years ago, the North Atlantic region would snap from deep cold to much milder conditions in just decades or even years. Winter sea ice would retreat, storms would change their tracks, vegetation zones would leap northward. Then over centuries the system would slowly sink back into cold. We still debate the exact mechanisms, but they seem to be tied to the ocean's conveyor belts, those great currents that move heat around the planet. A pulse of fresh water from melting ice, a shift in wind patterns, and the circulation reorganizes. When it speeds up or takes a different route, the North Atlantic gets a sudden delivery of warmth. When it slows or reroutes, the cold returns. If you were a band of humans or Neanderthals living in Ice Age Europe, these weren't abstract patterns. They were the difference between a landscape you could hunt and one you couldn't. In a warm phase, forests would open, game animals would move in, rivers would run differently. You could expand, split your group, send scouting parties into new valleys. Generations might grow up thinking this was the new normal. Then the circulation would flip again, winters would lengthen, snow would linger, plants and animals would retreat. Suddenly the hunting grounds your grandparents relied on would be empty, and survival would mean moving, innovating or negotiating with neighbours for access to better zones. Layered on top of these warm spikes were even more brutal episodes. The Heinrich events. Every so often massive armadas of icebergs would break off from the great ice sheets in North America and drift across the North Atlantic, dumping their cargo of rock and fresh water. The ocean surface would become colder and fresher, currents would falter or rearrange, and downwind climates in Europe would be thrown into chaos. In the cores, you can literally see these as layers of sand and gravel, stuff that doesn't belong in the deep ocean, raining down from melting bergs hundreds of kilometres from shore. To the people on land, these Heinrich events likely meant sudden, harsh deteriorations. Cooler, drier conditions, grasslands turning back into tundra, forests thinning out. Populations that had ridden a Dansgaard-Eschger warm phase into marginal territories would find those margins suddenly unlivable. Taken together, these abrupt swings meant that the last glacial cycle was not a static backdrop of cold. It was a world that repeatedly yanked the rug out from under its inhabitants. And this is the world in which fully modern humans perfected their survival strategies. In Ice Age Europe, our species eventually spread into territories long dominated by Neanderthals. They learned to work reindeer, horse and bison herds across vast seasonal ranges, following migrations that themselves tracked the shifting climate pulses. They refined clothing and shelter using tailored hides, bone needles, sewn footwear, and tents or semi-permanent structures that trapped scarce heat. They developed flexible toolkits, blades, points, specialized scrapers and burins that could be reorganized as hunting targets and raw materials changed. They decorated some of those tools and the interiors of caves with images and symbols that may have helped encode knowledge about animals, roots, and seasons. In Siberia, human groups pushed into environments that, at the glacial maximum, were closer to the Arctic than to anything temperate. Here, adaptation meant mastering permafrost, long periods of darkness, and powerful winds. Mammoth steppe ecosystems, rich in large herbivores, offered calories but required coordinated hunting, food storage, and social support networks that could bridge the hungry months. Across what is now the Bering Strait, those same skills carried people into Beringia, a cold but relatively productive grassland world. For thousands of years, this exposed landmass may have been both corridor and homeland. Some models suggest that people lived in Beringia itself for long stretches, buffered from the worst extremes on either side. At some point, exact timing still debated, descendants of these northern populations crossed from Beringia into the Americas, moving along ice-free corridors or coasts opened by regional warming and retreating ice. Once there, they fanned out with astonishing speed, adapting on the fly to everything from temperate woodlands to high-altitude plateaus and tropical forests. Every step of that journey was constrained and enabled by the last glacial's mood swings, when sea level was low enough, when corridors were passable, when food webs were stable enough to exploit. Then, about 20,000 years ago, the last glacial maximum reached its peak. Ice sheets were at their greatest extent. Sea level sat more than 100 meters below today's. Deserts were often larger, rain belts displaced, and many human groups were huddled in climatic refuges, pockets of relative mildness along coasts, in river valleys or at certain elevations. From this point, the long ascent out of the Ice Age begins. Between 19,000 and 11,000 years ago, global temperatures rose in fits and starts. The great ice sheets thinned and retreated. Sea level crept upward, then surged in pulses as ice dams failed, and meltwater lakes drained catastrophically. The world's map shifted again. Beringia drowned, Sunda fragmented into islands. Coastlines advanced inland by kilometers, sometimes tens of kilometers over human lifetimes. Even this warm-up wasn't smooth. There were reversals, like the Younger Dryas, a sharp return to near-glacial cold between about 12,900 and 11,700 years ago, likely linked again to disruptions in ocean circulation. For people trying to settle into more regular patterns of foraging, planting, or herding in the Near East, this must have been a shocking reminder that the Ice Age wasn't quite finished with them. And then, around 11,700 years ago, we enter a new phase, the Holocene. Compared to the last 100,000 years, the Holocene climate looks strangely calm. It has variability, droughts, wet periods, regional shifts, but the wild Dansgaard-Eschger-style jumps vanish. Global temperatures hover within a relatively narrow band. Sea level rise slows dramatically and then stabilizes. Ice sheets retreat to something like their present footprints. This is the plateau on which farming takes hold. In the Near East, people who had already been tending wild stands of cereals and managing herds through the late glacial and Younger Dryas now found a climate stable enough to make real bets on fixed fields and permanent villages. Seed selection, irrigation, storage. All of these long-term investments only make sense if next year is likely to resemble this year in broad outline. Similar stories, with different crops and animals, unfold in East Asia, in the Americas, in parts of Africa. Independent centres of domestication appear, each riding on the same basic support, Holocene stability. Dense societies, towns, then cities, then states depend on planning horizons that stretch beyond the next abrupt climate crash. Bureaucracies, written records, monumental architecture, and all the things we usually mean by history emerge in that window of relative calm, between about 10,000 years ago and today. So did the 100,000-year rhythm trap human history? Or did it merely set the stage? In one sense, it was a trap. For nearly 1,000,000 years, that slow glacial pulse repeatedly reset the board. Populations expanded and then were squeezed back into refuges. Technologies blossomed and then were abandoned as resources vanished or routes closed. Any early stabs at domestication, at large-scale settlement, would have had to fight against a background of climate volatility that could erase whole ways of life in a few generations. But that same cycle also forged the capacities that made our recent history possible. The genetic and cultural adaptations carved out in the cold, our social flexibility, our ability to cooperate in large groups, our knack for rapid innovation under pressure, were all honed in those glacial swings. The last cycle, with its abrupt Dansgaard-Eschger and Heinrich events, was an especially intense training ground. When the Holocene finally offered a long, relatively even playing field, our species arrived not as a blank slate, but as the heir to hundreds of thousands of years of practice in reading a restless planet. You can think of it this way: the ice didn't just delay history, it taught the students who would eventually write it. And as we sit here, in the latest warm chapter of that long 100,000-year beat, it's worth asking what it means to live at the crest of such a cycle, and what happens if we start pushing the climate in directions that rhythm was never meant to go. So what does that long, icy metronome mean for us, lying here in the quiet of the present? The best picture we have is this. The big ice ages are paced by the sky, but built on Earth. Subtle changes in Earth's orbit and tilt nudge the system. They decide how much sunlight northern summers get and where it falls. But those orbital cycles on their own are gentle. To turn a small nudge into a world with mile-thick ice over cities and drowned continents, you need amplifiers. That's where the Earth system feedbacks come in. Growing ice increases the planet's reflectivity, bouncing more sunlight back to space. Colder oceans draw down more carbon dioxide. Colder air holds less water vapor. Vegetation shifts, dust changes, ocean currents reorganize. Each piece leans in the same direction, and the climate slides into a new state. Orbital pacing plus ice, oceans, carbon and biology, all linked in slow looping chains. We understand the outline of this story fairly well, but the details are still full of open questions. Why exactly did the world switch from 41,000-year ice ages to 100,000-year ones? How much of that was ice sheets changing their own mechanics, and how much was deep ocean circulation or long-term carbon cycle tweaks? Why do some orbital configurations trigger huge glaciations, while others just don't? As for us, we are not waiting for the next slow glacial descent. On orbital timescales, we should still be in a relatively stable warm phase. Instead, in just a couple of centuries, we've pushed greenhouse gases and temperatures in a way that usually takes thousands of years, sometimes tens of thousands. Natural cycles are like the ticking of a long clock. Human-driven warming is more like leaning on the gears. The planet will respond with the same physics as before: ice, albedo, oceans, carbon. But on a compressed human timescale. Coastlines will move, rain belts will shift. Some regions will become easier to live in, others much harder. Our ancestors rode these shifts with feet and fire and stone tools. We face them with satellites, cities, and billions of people tied into global systems that don't like abrupt change. If there's a quiet lesson in the ice, it's that the climate is neither fragile nor fixed. It is powerful, and it moves in patterns we can learn, but not ignore. We are the descendants of people who survived swings far harsher than anything in recorded history. The same adaptability that carried them through glacial chaos is what we'll need now. Cooperation, foresight, a willingness to adjust before the ice or the heat forces our hand. If you'd like to drift off with more of these buried stories, I've put together a book about prehistoric secrets and the worlds that shaped us. You can learn more and find out how to get a copy at sleepytimehistory.com. When you have a moment, you can help this channel grow by tapping like, subscribing and leaving a comment. If you feel like sharing, tell me where and when you're listening from. City or countryside, late at night or early morning. It's a small way of mapping our own little human pattern here at the crest of the cycle.